All right, so we've got an ideal air standard Otto cycle with a compression ratio of 8, and we're told the conditions at the beginning of the isentropic compression process, so that would be at state 1, and then we're also told the compression ratio and the amount of heat that's added per cycle, so that would be the Q input to that cycle or the heat added from 2 to 3, and that's 800 kilojoules per kilogram. So we've got everything in given, find, assume format. We're ready to go on with our solution. So the first thing you need to do is figure out what your governing equations are. So let's start with the thermal efficiency. On your equation sheet, this is written as big W net out over big Q in. So it's kilojoules on the top, kilojoules on the bottom. But since we're modeling this as a closed system with air, piston cylinder closed system, we could divide the top and the bottom by the mass, which does not change. And we get things in terms of little W net out and little Q in. So kilojoules per kilogram on the top and the bottom. And the work net output is any of the work output for the cycle minus any of the work input over any heat added for that cycle. And if you look back, if you review the video on the Otto cycle, you'll see where we got these terms. So by applying the first law, for example, for the workout, by applying the first law from 3 to 4 to the process from 3 to 4, we see that the work output is U3 minus U4, and of course Wn is U2 minus U1. And Qn is something that we're given. So that's our governing equation for the thermal efficiency. And the mean effective pressure, well, on your equation sheet, it's written as big W net out over the maximum volume minus the minimum volume. And once again, since we are talking about a closed system, I could divide the top and the bottom by the mass, which does not change during the entire cycle. And I'll get things in terms of little W net out over the maximum specific volume minus the minimum specific volume. Now, the maximum specific volume is going to be at the beginning of the compression process, and the minimum one is going to be after the compression process, so V1 minus V2. With the Otto cycle for each of these processes, that piston cylinder, the volume is going between maximum and minimum. So the piston head is moving between top dead center and bottom dead center. So V1 minus V2. And then, of course, since I know work net out, I already have that for my thermal efficiency equation. I bring that on down, and I just rearrange V1 minus V2 into something that's a little bit more convenient because I could put that V2 minus V1 in terms of the compression ratio, which I'm given. All right, so with all that information, I've got my governing equations for the two things I'm supposed to find, and now I just need to plug in the stuff that I know about the state. So at state 1, I do need the specific volume, and I can calculate that with the ideal gas law, because part of air standard assumptions is that we've got air as our working fluid and it behaves as an ideal gas. So if I plug in the numbers, making sure that I put the temperature in absolute temperature units, I get 0.8323 meters cubed per kilogram. Now I need to go to my ideal air tables, which is an A22, to get my U value, and that internal energy value is read off at 290 Kelvin, which is on the table, no interpolation needed. Now I need to go to state 2, and part of the, how you work your way around these cycles is figuring out how state 2 is related to state 1, or maybe state 3. How is it related to the states before and after it. And from 1 to 2, you have an isentropic compression of an ideal gas, so you can apply an isentropic relationship for an ideal gas. And that's convenient because I know the ratio V2 over V1 is just 1 over the compression ratio R. So I do need to get VR1 from my ideal air tables for state 1. And when I plug that in, I get my relative specific volume at state 2, 84.5125. And all I need to do is look at my ideal air tables and interpolate for the corresponding internal energy value, U2, at VR2, which is 475.11 kilojoules per kilogram. So that's, once again, it's A22. Now I need to go to state 3. So I've got all the stuff I need for state 1 and state 2. I go to state 3. Now, between 2 and 3, I do not have an isentropic process, so I can't apply an isentropic relationship, but I do know the amount of heat that's added between 2 and 3, so I can apply my first law and get an equation for U3. So U3 is 1275.111 kilojoules per kilogram, and now I'm ready to go on to state 4. Now, for state 4, from between 3 and 4, you do have an isentropic expansion process. You have an isentropic process, so you can use an isentropic relationship for an ideal gas. And you may wonder, well, I don't know, but I knew V1 over V2 or V2 over V1 when I was figuring out V2, but Do I know V4 and V4 over V3? And the answer is yes, you do, because the process from 4 to 1 is a constant volume process, and 2 to 3 is a constant volume process. So V4 over V3 is equal to V1 over V2, which is just R. So I do need to get the relative specific volume at state 3, and I'm going to have to interpolate on those ideal air tables in table A22 at the internal energy U3 that I calculated just a second ago. So interpolating, I get a VR3 of 6.108, and if I plug that in and solve for VR4, I get 48.864, and that can be used to calculate what my internal energy, and I'm sorry, there should be an equal sign in between those two, but my internal energy at VR4 is 588.737, and then if I plug everything in, I can calculate my thermal efficiency and my mean effective pressure. All right, well, I hope that was helpful. Thank you for watching.